Hello, welcome to this session on containers, pulling the lid off, where we're going to take a deep dive into the underlying technologies that make containerization work. This is going to be a very fast-paced session. You're going to want to listen at 1x. I'm your presenter, Ken Sipe. I've been working with Docker since 2013 when the first bits hit GitHub. I started with version 0.3 and been using Docker ever since. Prior to that, I was a Linux head, so I have some of the understanding of the underlying technologies and looking to present some of that with you today. Here's our agenda. We're going to take a look at containers at a high level, and then we're going to take a deep dive into the container runtime, and then the underlying technologies, which are CGroups, Namespaces, and CGroups. So what are containers? Well, the initial understanding of containers at a high level is that it feels like a lightweight virtual machine. There's definitely a level of isolation that's occurring here. We can isolate at the process level, in other words, the PID count. We can isolate at the network level, among other things. This is highly configurable, but oftentimes when you use a containerizer, some of those opinions have been chosen for you, and then you're just left with configuring some of those options. It also feels like chroot on steroids. Now, this would be somebody who really knows and understands Linux, but when you chroot something, you don't usually get additional isolations like PID. So what are the differences then of containers and virtual machines? Well, it might be best to look at an image. What we see here is we illustrate the differences. On the left, we have virtual machines, and for a virtual machine, you have a whole nother guest OS that's sitting on top of a host OS. So there's a lot of resources that are consumed in order to spin up the thing that you're most interested in, which is the application themselves. On the right, you see what containers look like. We don't have a guest OS. We just have the host OS. We have a container engine that might be involved. This depiction shows Docker, but it could be any containerizer. And applications then are running on the host operating system, and they are isolated, but they don't have the same level of isolation that a virtual machine would have. So the cons of using a container is that it has weaker isolation. The pros of it, though, is that the container runs at near native speeds, and it has much less memory and resource costs, and the startup speeds are insanely fast. When we look at virtual machine spin-up times, they're usually in the tens of seconds at a minimum. Of course, depends on platforms. With the same platform, containers spin up in fractions of a second. This is a historical diagram. It's not exactly true today, but when Docker first came out, it sit on top of LXCs and libcontainer. But look at the underlying technologies. CGroups and namespaces have been depicted as part of the architecture from the start. And it's true today. That portion is true today. So when we look at the underlying Linux container technologies, the things that we're going to illustrate and dive deep on today is CGroup, namespaces, and CGroups. The important thing to note is that if you're on Linux, you're technically always running in a container. So if you think that you could run at native speeds faster than in a container, that is not true. You're always inside of a container. You're always inside of a namespace or a cgroup, even if that is root. Let's look real quickly at the Docker runtime and understand some of the details there. So as we see here, I'm looking at the PIDs of a host on an Ubuntu instance, and you can see all the PIDs that are there and the processes that are running. And then when you look 3/4 down the page, we can see I did an ls on my local file system. I run Docker on Ubuntu, or with Ubuntu on Ubuntu. And you can look at the PIDs now. If I look at PS, I just see the 2 PIDs. If I do an ls, I see a whole new file system. This is what we would expect. And we're going to also build out as part of a demo from scratch, not using Docker. First, let's understand chroot and see what that provides and helps us with. So the first is a little bit of an understanding of chroot, what it does. All it does is change the root file system, and there's details that we don't need to go into here, but you can follow up. So a quick demo, we're going to make a directory and then essentially create a bootstrapped environment in that directory for Focal, which is the latest version of Ubuntu. And then we're going to chroot into that space, saying that I want to run bash, leveraging the new root file system. Here we can look at the file system that I'm on. I'm on Ubuntu. I'm looking at a pwd, which is where am I at. So the current directory is my home directory, which is just ksite. And then I go in and I say chroot. And as I chroot bash onto a new file system, a new operating system, essentially, it's the file systems that make up an operating system, I should say. If I change directory, do an ls, you'll see there's nothing there. If I do a pdw, I'm actually rooting this space. If I do an ls on home, you'll notice that there is no ksite. It doesn't exist. So it appears, even though I'm on the same operating system, that I'm in a new world that has a whole new space to it, even though I'm still on the host operating system. Okay, so that's the core core of chroot gives us this world and this view that helps us understand that I can actually overlay a file system. What you want to know from a Docker perspective is that when we pull Docker images, they're just tarballs, and I have a tarball that's landing inside of a directory, and then I'm chrooting into that space. So we do leverage chroot type technologies when we're using containerizers very commonly. Let's dive into namespaces real quick. As you see here, we have different types of Linux namespaces. You see them identified at the very bottom, and I will dive through them. I'm not going to spend as much time because I want to get to the demo. So the slides are going to be a reference and a resource to you. But there are 6 different namespaces that you can define within the Linux space: PIDs, network, mounts, UTS, IPC, and user. The important thing when we talk about containers is that I want to be able to isolate my PIDs, and I want to isolate the PIDs seen in the container, but I also might want to control what the host operating system sees as well. When I have a mount, I can mount with different styles. So I can mount with a read-only, a shared, a slave, or a private. Now what I mount with a private means is that within my container space, no other container nor the host can see this. It's just mine. So how might we see this being used in the container world? Well, we could mount a read-only space for the user. So now I'm gaining all access to the libraries associated on the host operating system, but I'm doing it in a read-only space, so nothing can write to it. I can also have a private temp space. So I get my own swap space, my own temp space. Anything I write that would write to temp would not be seen anywhere else. It's my own private mount. And then we can get into some of the details of network and such. As I mentioned, I'm going to blow through some of this fairly quickly in order to get to the demos to illustrate some of these underlying technologies, because the slides are great as a reference, I think, but actually seeing it in action is going to make a whole different impression. We are going to be, as part of the demo, going through UTS configuration. So that just basically means that I can get the host name or set the host name, and that will be different than the host name of the host itself. And that may seem a little strange, but this is part of the abstraction layer that we want to dive into. The important thing also about namespaces is that it's just like a file system in the Linux space where I can define where all my procs are. Everything is managed what appears to be a pseudo file system in the Linux world. But the namespaces are defined on that file system. So I could go into proc, which you see here, proc, whatever the PID is, and slant ns, and I can see what namespaces are defined for any process. So if you see here, I have just a PID that I pulled out. I just pulled out some random one here, this PID 39783. And I said, do an ls on that. And you'll see that I have in that directory a number of folders that help identify in detail what is associated with that PID. So here I have ns defined. I do an L here in order to get the symlinks displayed. And I can see I have a C group that maps over to this C group with a defined name that defines the characteristics of that particular process on this host. It's also useful to realize that if I have a namespace, in particular, if I have a namespace defined for a process or a container, I may want to go into that namespace to understand its view of the world. And so I can do that with a utility in Linux called nsenter. So here I've just done a help explanation on nsenter so that you could see it. But usually you either want to define your own C group for a given namespace, or you may want to just target a PID. So I can just say, hey, I want to enter the namespace for this defined PID, and now I can actually enter into its world. I'll then have my network, my PIDs, everything will be defined as relative to that particular process for its namespace. So that's namespaces. Namespaces, the important takeaway for namespaces is that it provides isolation, and the focus is a view of the world. How do I view the world? How do I understand the world that I'm living in? The next section that we need to talk about is control groups. Now, control groups, where namespaces define a level of isolation, control groups provide accounting and controls. What are the constraints that I want this process to live under? So the types of controls that we can have defined within Linux go beyond what you would normally see in the Docker world. Here I can actually provide auditing and accounting, if you will, in memory, as well as CPU. I can get limits on memory and CPU. That's probably what we're used to. But I can also provide limits on block I/O and network and a variety of other things. Most of the details associated with control groups are in sysfs C group, and that will define a hierarchy of trees underneath of it for the different categories that we just talked about, and then a given PID will be in one of those subgroups. I think that will become clear with some pictures. So here I'm in CoreOS, and in CoreOS I'm doing an ls on top of the sysfs C group folder space, and you can see the exact configurations or types of C group controls that I can have, as we talked about. So you can literally see it on the operating system, on the file system. And then what happens is that for a given CPU, I would have a name, and that name might have subcategories, but I'll have a PID associated with that given constraint. So Bitcoins, there's a process 42, which is in that C group. I have Hadoop that has 2 PIDs within its C group, and then I have memory defined. And what's important is that that PID, say 42, can only live in CPU once. In the subtree of CPU, it can live there once, but it might be posted somewhere else, like under memory. And so for each category, you would have a PID for its controls. And then on the right, you see how the resource management within the Linux space manages those details. So let's take a deeper dive then into the control groups for memory and CPU, the things we probably most care about. So the first is that we have memory C groups for limits. And the limit could be soft or hard for most operating system, and it is an operating system configuration. It's going to be hard, which means that as soon as I've hit the upper bounds of that limit, then I'm going to have an kill or an out-of-memory reaper that comes through in the operating system level that kills a process because it's violated its constraints. So here, in order to demonstrate that, we could say Docker run this image, which is Ubuntu with Bash, with a limit of 128 megs. When we see an out-of-memory situation, if it's not inside of Kubernetes, the way that you would evaluate that is actually at the operating system level, the host level. So here we're using the journal control to look at the transport, and we'll see that there was an killed here for this particular process, this container in this particular case, and we can see the details of it. So again, this is very low level inside the operating system at the host level. I can look at the journal. When we look at, we just went through memory, looking at CPU is a little bit more challenging because there are actually 2 options, one CPU shares and one CPU sets. When we look at CPU shares, the way that you would look at this is almost like within threads, you have a nice value or some kind of prioritization value. So there is a priority weighting that's associated, and the default for most operating systems is a K, so 1024. And so here you can see that I'm running Docker for this particular image, and I'm setting the core to 512, which is half a core, basically. Well, it actually depends on the number of processes running in their containers that are living within that defined C group space, and they will share based on their weighted value. That's really the technical details there. It is possible to create our own shares, again, getting very low level at the operating system level, where I can say CG create, and I'm going to create a CPU A and a CPU B, and then define different levels of share that's possible within that C group. And then all I'd have to do is create a process and assign it to that particular C group. And then you have the weighted balance that you see here. Now that's assuming that these are the only 2 processes living within that C group space. The other option that you have for C groups with CPU is CPU sets. Now CPU sets basically pin a core. So what I'm seeing here with this Docker run is that I'm setting core 0, 4, and 6 to be the 3 cores that will be associated with this process. There's a couple of things to note here. This is really great for things that are NUMA or have a high hit rate within the CPU cache, and you can get added value by pinning to cores. But I'll also add here that no container orchestration engine that I know of uses CPU sets. It's very challenging to manage for a variety of reasons, and so CPU shares are the things that you want to be thinking about when you're using, say, Kubernetes or other containerizers. The thing to note within this space is, again, this is defined within sysfs C groups, and it is a pseudo file system. So a couple of tools that are useful to know. One is systemd's signals. So this is CGLS. This is a way that you can get an LS on the file system associated with C groups. So here you can see where memory is defined and the PIDs that are defined for it. And this is an example I took from years ago where I was working a lot with Mesas, where we had a given slave and frameworks running and things of that nature. Another option for you is to look at or cat the proc PID for C groups. So every PID, when it's created, will land into the proc folder. And in the proc folder, here in this example, 9674 is the PID. It's going to have a file called C groups, and then you can see the different configurations that you have for each of the different types. So you can see that we have CPU, and we have CPU sets, which are not even set. We have memories defined, and things of that nature. There's another really great tool, probably less known or understood if you're not in the Linux space, is systemd CG top. So this is essentially C group top, or it's like top for C groups. So I can actually pull this up, it will list, and based on whether you key in that you are interested in CPU or memory, you can change the order what you see at the very top of it is the thing that's consuming the most. In this particular example, we're seeing the top of CPU, but defined by CGroups. And this can be very valuable information to understand the lower level details of what's happening inside the container. As we pull together all of the details and we start talking about container or Docker container with CGroups, one of the things to note is that under the sysfs cgroup folder space, we'll have a system.slice where I have Docker dash and then whatever the unique container ID is for that system. So under that, I can do an ls for that file system, look at the Docker and see all of the details on how the CPU is set, what the memory configurations are, things of that nature. So let's go build a container from scratch. Well, diving into our demo here, what we're going to do is create our own container, and we're going to create that in Go. So hopefully Go is readable and easy to understand. You're going to see how easy it is. It's important to note that I am using Linux libraries, and this will be Linux-specific Go code. I also want to call out this was inspired by the great and famous engineer Liz Rice, who gave a talk at GoTo some years ago, and there's been some modifications to that, but if you want to see her whole presentation, which is dynamite and worth a look, there is the YouTube video for that. Additionally, this is the GitHub repository where she provided a lot of the code that we're going to walk through. You're going to see some definite differences associated with my code. It's either based on some cgroup changes in the operating system I'm using or some advancements that have happened or a variety of other reasons. So our code is going to be over here. Over here, I have two different terminals, which are also on Ubuntu. I'm going to do a Docker run. In this space, this terminal is kind of in the code space over here. So you'll see me running the Go code from over in this terminal. Over here, we're going to be experimenting and looking with the operating system. And the thing to note is that I may want to do an ls and grep docker. So you can see that I just have two Docker folders within my cgroup space that's defined. I'm going to spin up Docker real quick, which by the way is what we want to do with our program. We want to say, go run this application, run some kind of thing we want to run within that container. Here you can see that I have a whole new file space that I'm on. It's not my host operating system. You can kind of see that by this using the container ID here. You can also see I'm root within that container. But what's different here is that I drop in here, you can see a whole new folder that was created. I can do an ls on Docker and autocomplete, and you can see that there's a whole new file system that was created for our cgroups for that particular running instance. Let's get into the code. Let's do that by exiting out of our container. And then say I want to do a get checkout of version 2, which is the next level that I want to advance to. We'll see some code changes that happen over here. So what we're looking to start us out is I want to be able to say go run this main, run echo hello world. And so since we're going to get a run as our first argument, I'm going to create a switch here where I'm going to run, and then I'm going to panic if anything else happens. And then I'm going to just simply print out the thing we're trying to run at this point. So we're not actually even executing anything. So if I say go run main, say run this, and it says, hey, I'm running this. Or I could say run echo hello Jones, and then I get an output. So hopefully that code is reasonable and understandable. We see one evolution of I've got a Go program that can execute something. Currently it's not executing it, we're just outputting and providing logs. So let's switch to V3. We'll see some code changes over here that modify. We want to be able to run this, but now we want to run bash. So here I have to make a few changes. I'm going to execute this command, which is I'm going to run whatever this first argument is. And there could be other arguments that pass. This is just pulling out everything that's after 2+. This is pulling out 3+ and then expanding them. So not a big deal. Here we have a command, and I have to stitch together the operating system standard in, standard out, and standard error, and then I'm going to run it. So let's see if we can get this to work for us. I'm going to say run, but this time echo hello Jones. So now you see the output of the print line, but here we see an actual execution of the echo, which means hopefully we can go in here and we can also say I want to bin bash. So now I'm actually inside of another bash shell. And so I've created a shell that I went into. You can see that the command line changed based on the fact that I went into that shell. And that's it. I'm actually running something. Now, I'm running something as part of the current operating system. If I see PS, you'll see that I get listed in there. Go ahead run, and there's a main, and there's a bash. I can exit out of it, and then I'm out, and no longer am I running Go. So that won't show up in my PS listing at all anymore. Let's switch to version 4. Now we want to start containerizing. We've actually spun up a process, but now we need to containerize that process. So let's look at step 4. Step 4 here, which is listed here, step 3, set namespace. We want to be able to change the host name. Now this is going to change because of this. I'm going to actually have a need to run this as root. But here I'm going to run, and we're doing nothing more than I've added in one extra line. I realize it's 3 lines. It could be, separated in 1 line. The point is, I'm going to change the details of the namespace. So I'm going to change the clone flags for the proc that's going to be created to say I want to clone a new namespace for UTS, which is where we define our host name. So now that we have the code changes, the one simple code change from line 38 to 40, I can go in here and let me paste the execution we want to run. And now we can see I am inside of a container, kind of, right? I'm beginning to see the semblance of it. If I ask for the host name, you'll see that it's the same as the host name for the host. But I could also go in here and say that the host name is container. And now if I say host name, it is container. But if I come here, if I ask for the host name, it's still the host name. So now we're providing some level of namespace isolation that we didn't have before. So that is the next step. Let's exit out of our current container and switch to version 5 of the demo. Let's look over here in code. Now we have a problem, and the problem is that I want to be able to run and I want to set the name, the host name of the container. Now ideally I would want to run it down here. Like it has to be a process that's running, and that process has to be in its own namespace, if you will. And so ideally I would call it here. The problem is that this is a blocking call. When I'm running a process, it's blocking, so I won't even hit this until I exit out of the newly created container that I have. So we have to find another way, which means I need to make this process reentrant. So here I'm going to add a child command, which is not going to be called by us directly. It's going to be called indirectly, and we'll see that in a second. So here I'm going to call a child process. So our run is still the run. I'm going to change run now, and what I need to do is I'm going to execute the command proc self exe, and that will basically say that I want to run myself. I want to run an instance of myself. But in this case, when I'm running myself, I want to be able to pass in child as the first argument. There's a little bit of Goism happening here where I'm going to append to an array a child at the head of that array. I need to expand out everything that was there and then expand it out. So that could be a lot. You can hit me up later as to the details, but essentially I want to call the process, my process again, and I want to call it with child, which means now that I can set up the container like I did before, but now the container is up and running. And so since I have this container running and I'm re-entering my process call, I can then make the call that I want to make on the child call. So I have argument 2, which again was probably bin bash, but we could do whatever we want. We could also pass in arguments. And then I'm going to, before I hit run, I'm now going to call the set the container name. So in this case, I'll call it container. So let's do that. Going to call this one more time. And if I look at the host name, you'll see that the host name is already container, where this host name is its original host name. So now we've created a container space, and the container space has a brand new host name, and we provided some level of isolation within this container. Let's exit and go to the next level of the demo and switch over here. What we want to do now in our next step is we want to be able to manage the PIDs. And so if I were to run the prior example one more time, I'm already here, so I'm going to stay here. What we would see is that the process spaces are not isolated. They're not isolated at all. So the host can see the child, the container's PIDs, the container can see the host PIDs, and we need some level of isolation. So we are going to take a multi-step approach at that. The first thing is that we're going to add to our clone flags that we want to add a flag that says I want a new PID space. And since we're doing that, we changed our logging now to say that I'm running some command, but I'm running it at a given PID, and you'll see that repeated as the child and the run. So you'll see that outputted twice because we will create new PIDs as soon as I spin up a new instance of a thing. The first run is on the host, the second run is in the container. And that's all we're doing so far. You can see a little bit of getting the OS get PID. You can see that twice. Well, let's run now. Let's run this command. You can see that it started up at this PID on the host, but inside the bin bash is actually running at PID 0. However, if I look at PS, you'll see that I don't have the PID isolation that I'm looking for. So we've gotten somewhat there. I've actually created another PID. It now newly exists within the container. But what we have to understand is the details of how PS works. PS works by looking inside of the proc folder. If we were to look at, say, well, let's look at it this way to help understand this. If I were to do an LSL on proc and say self, what we're asking is ls when I run it, I want you to print out what's in that folder for myself. And you'll see that, oh, it points to a given PID. And every time I run it, it's a new PID because the process starts up and it dies. And for that moment in time, its PID number was this. But you can see that all of the PIDs are in proc. This will be a lot, but all these numbers represent our PID space. So that means that we need to have folder isolation in order to do that. So we need to jump to our next demo, which is number 8. Details over here. I need to establish a root of the file system. So I need to have a file system with its own set of PIDs and things of that nature. And so the new change that came across now is that I am going to root into this namespace. But notice that this is, in the example I had on slides, this is opt, the focal fs, and that had all the downloaded operating system files in that particular folder. So that's all we've done so far. Let's run this and see where we're at, because it's not it completely, but it gets us one step closer. Now when I do a PS, we see a problem. I'm not mounted, so we need to add one more step here. But what I could do is say that I want to sleep for a very long time. At the host operating system, I can get a list of the PIDs that have sleep. You'll see that the sleep is here. I can do ls on the proc for that PID and look at its root. And what we'll see is if I do that again with sudo, you'll see that the root for that PID actually points to this new file system. So now we can, we're removing the magic. We can actually see that this PID, which is viewable from the operating system, has a root, and that root is defined in a wholly new place. But as you see here, I'm still not able to do a PS. So let's take this demo one step further. Version 9, we need to mount our proc. Let's go down here a little bit and look at a few new details. There's a couple of things that have been added in. The thing I want to call out real quick is this mount. So I'm doing a mount of proc. That is going to actually mount us into that file system space. And of course, after the run of the container exit, I want to unmount that space. So we're being good citizens here. Additionally, there's one more thing that we could probably remove for right now, but this is, we want to unshare some flags. And that basically says, I don't want the host operating system to know about this kind of mapping that we're doing. Let's go in here one more time and do a run of this container. And now we notice that we're PID 1, but notice that when I do a PS, because I have the mount in a new location, I have a number of PIDs that are represented here, but I am isolated from the host system itself. You see in my notes here, I could also do a mount of the proc, and you can see that that mount does not show up here. If I were to remove that line of code for the unshare, then we would see that the proc happens. So you can see that the unshared is that level of protection or abstraction from the host operating system. Okay, and then lastly, what we can do is I may want to actually control CGroups. So what we played with so far is controlling namespaces, which gives the view of the world of the process or the container that we're creating. But what if I actually want to provide some limits? So what we're going to do is take a quick look at how things are managed within the CGroup space, which we didn't go into heavy detail on. Let's run Docker real quick. And within the Docker space now, let's change directory to Docker and then whatever it is, and take a look. And what we can see here is that I have all of my CGroup controls within this folder that was newly created by the running of that Docker image. But I could do a cat, let's say, on, memory max. So if I look at memory max, it's set up to max. I can also take a look maybe at PIDs max. And you'll see that it has some limits there. Now, looking at memory max, let's switch this out. Let's run Docker with the memory constraints that we wanted set. So here, we have something slightly different. We have a new container, so I'm going to have to jump out of here and jump into another Docker instance. But if we do a cat on memory max, you'll see that setting this to 10 megabytes has now set this to the representation that represents 10 megabytes. So what we want to do now is we want to control PIDs. That's the thing that we're going to try to do with our code changes that we want to make. Okay, so let's exit out of our container. We are now going to attempt to control the PID count within our given controlled or given container. So let's make a few changes here. There's a lot to do here, so to speak. We've already seen most of this. The one change here is this PID CG. So here within the CG groups, I have that defined as to where we are to define that within the host operating system. We're going to make a directory called Go Container underneath the system slice. We're then going to write to that our PID max. So we don't want a PID max that's infinite. We want to be able to define it, and we're going to say that 20 PIDs is the maximum number of PIDs allowed within this container space. We're also then going to create a CG group procs, the thing that manages the processes that are within the CG group. And we're going to add ourselves to that. So we need the PID for ourselves added into that CG group. The rest of this is, for the most part, the same. We're going to set the host name and the chroot, and we're going to change to the current directory, which is undefined after you set chroot, so that was why that was there. We're going to mount the proc. The changes that we're looking at here is the PID CG group. So let's go through and run this process one more time. And what we'll see is under here, I will go into the system slice. You'll see a newly created Go container, and we can actually look at memory max and see that it is set to max. Oh, it's not memory max. We want to say PID max, and the PID max is set to 20. So we're going to do a pretty fancy and interesting thing here. We are going to take a look at a couple of things first. Let's look at running sleep again for a while, and then do a PS on sleep, and we'll see the PID. We can then go in and say, you know what, let me cat the CGroup PIDs procs, and you'll see that this PID is in there. So our CGroup procs have defined within our CGroup controls for the Go container. It's defined appropriately. Now the next thing that we want to do is let's stress this out. Let's see if we can test out our system. So let me exit the sleep, and what I'm going to type in here is what is referred to as a process bomb. So we're defining a function, which is colon. I'm going to create an instance of that is going to be in the background, and then I'm going to run it, and it's going to run itself, and it's going to run itself, and it's just going to create a bunch of processes. So you can see here that we're having problems, and the problem is that we have a limit on the number of forks that can happen. If I went in here and I said I want to look at the processes, what I would see is underneath our Go program, so we have our Go program right here, we'll have a number of processes that are running. This will never be greater than 20. But we could also see that the PIDs.current is 20. And so all of our constraints are built into the system now. Well, that was a lot to take in a very quick amount of time. Hopefully that illuminated like the underlying details of how a container actually works and runs in the Linux space. The details of that is that it started out with chroot, which allows us to mount a new file system that helps to provide process isolation with PIDs. It helps to mount a whole new file system, things of that nature. Second, we have namespaces, which can then control the view of the world. What is your network? What is your view of PIDs? Things of that nature. And what is your host name? And then we took a look at CGroups a little bit, took a little bit of a deep dive, looked at some of the tools that were there for providing that, as well as we provided a demo for PID maxes. So hopefully that was useful. I would love to get your feedback. There's how to contact me. Have a great day.